Alright, well, here is Thursday's pre-lecture video, even though we won't be together in class for a real lecture. So, in this chapter, we're going to be looking at electric fields and energy associated with those electric fields. And in order to do that, we want to review a little bit some of the concepts that we learned last semester. So first of all, we want to talk about work. Remember that work is when you have a force acting for through a distance. And we learned that work is defined by a dot product, which means that the dot product of these two vectors, force and distance, is equal to the magnitude of the two vectors times the cosine of the angle between them. In the cases where your force might vary over your displacement, we can write it as the integral of f dot ds. Now, one of the things that we learn is when you talk about a force doing some work, like for instance gravity or a spring, we see that as a result of the work done, there's a change in the potential energy associated with that force. And what we see is the force does work, its potential energy decreases. And remember, we think of potential energy can also be thought of as stored energy. Now we're going to apply some of those ideas to the electric field. So here in this situation we have two parallel plates that have equal and opposite charge. Because of that, an electric field is set up between the two plates, and the electric field is uniform and facing in the downward direction. We know that if we put a charge, like right here is our charge Q naught, if we place that in the electric field, it's going to feel a force equal to Q naught times E. Now, if we want to think about the work done on the charge, well, the work done is going to be found by the force times the distance. The force is QE, which in this case is in the minus y direction. If we call this, this is minus y, this will be in the plus y direction. And then when we think about the distance, what we're going to say is going to be the displacement in the y direction, which in this case is also going to be in the minus y direction. What we find is, because of the fact that the force is strictly in the negative y direction, it doesn't matter if the charge actually moves along these dotted lines, because the only displacement that's going to contribute to the work is going to be the displacement that's parallel to the force. Remember, that's what the dot product means. And so the total work is going to be QE times delta y. If we allowed the charge to move from point A to point B, from the top plate to the bottom, then the total work done would be QE times the total distance between the plates, which is just D. Now we want to think about what's going to happen to the potential energy. So really the force that we're talking about, the F equals Q naught E, is the force that the electric field exerts on the charge. And then it's moving the charge. And of course we saw that as it moves the charge, it does work. And remembering what we learned from the previous semester about work and energy, this ended up in a decrease in the potential energy, or the stored energy that was stored in the electric field. This really means that the final potential energy is less than the initial potential energy. And of course, this represents the positive work. And I'm saying it represents the positive work just because the work is positive. And remember, the potential energy is the energy that was stored in the electric field. So that kind of helps us think about what's going on. So we see that as positive work is done, we go into a decreasing amount of stored energy. Now, thinking about that allows us to sort of look at some special scenarios. For instance, when we think about the positive charge moving in this electric field, so say the charge went from point A to point B, the work that was done was equal to QE times delta Y. And that's a positive amount of work. The other thing that we can see is that because positive work is positive, then we know that this equals minus the change in potential energy. And so the potential energy decreases. If you think about it, this is just like a ball rolling down the hill. The ball goes down the hill because the force of gravity pulls the ball down the hill. And notice also it goes to a lower potential energy. What we're going to see, to make a more general case, is that this is something that's going to happen naturally, because when I place this positive charge in this electric field, it does feel a force down, and so it will naturally move in the direction from A to B. It turns out the way that it naturally moves is in the direction that's going to cause its potential energy to decrease. Remember that and think about that. Now, what if we look at the different situation? What if we have the particle moving in the opposite direction? What if it goes in this upward direction? Well, we can think about the work. So work is the force times the distance. Now, the force that's acting on that positive charge is still my QE. And just to be clear, we'll write that it's in the minus J direction, because this is the minus Y direction. Up is the positive Y direction. But the displacement we're talking about, the delta Y, is actually in the positive Y direction. So when we do the calculation of the work, we actually find that in this case the work is negative. And so this is also equal to minus the change in potential energy. But if this is negative, then that means that the change in potential energy is actually greater than 0 because of the negative sign. And so when it moves in that direction, the charge moved so that its potential energy increases. But we know that that couldn't have happened spontaneously, because the charge would have felt a force downward due to the electric field. So there had to be some sort of external force making the charge move up. And so that force was what had to do some work to make the charge go up, and that's what ended up allowing it to have an increase in potential energy. It would have had to be increased by the work done by that external force. Similarly, if we look at a negative charge and we think about it moving in the direction of the electric field, now let's find the work. Okay, remember the electric field is down still. So my work is equal to force times displacement. This is minus Q times E, and that's in the minus J direction. My displacement is delta Y, and that's also in the minus J direction. But if I'm careful, I notice I have 3 negative signs, so this work is negative. This is similar to the example we just looked at, and knowing that work is equal to minus the change in potential energy, because our work is negative, our change in potential energy is actually positive in this case. Again, notice the charge did not move in the direction the electric field would make it move. An external force would have to move it that way. Again, the idea that because the force that the charge would feel due to the electric field would have been upwards, it actually moved in the opposite direction, which means, again, some sort of external force downward would have had to be applied. And because that external force was applied, that's what allowed it to increase its potential energy. Finally, let's allow that charge to move in the upwards direction. Now let's see what's going to happen. So now my negative charge is moving in the opposite direction of the electric field. So the force that it feels is going to be in the upward direction. Oh, sorry, I got too many. So the force is going to be in the upward direction, and then the displacement is in the upward direction. And so the work done is positive. And so the change in potential energy is actually less than 0. Again, this is the way it would move spontaneously without any external force. So again, the idea here is that if we allow it to move in the way that it wants to, spontaneously in this electric field, it'll naturally move to a direction of decreasing potential energy. While when we have to apply a force to make it move in a certain way, that external force ends up putting energy into the system, and that's why it can move to a place of higher potential energy. So basically, what we generally find from these 4 different cases is if an object moves spontaneously in a particular direction, it's going to move in a direction that its potential energy will decrease. Think of this example, rolling down a hill. If I put a ball on the top of a hill, it is going to roll down the hill. We know it does that because of gravity, but we also can recognize that it's going to go to a place of lower gravitational potential energy. Its potential energy will decrease. If we use an external force to make it move in a particular direction, then its potential energy will increase we could think of pushing a ball up a hill. The ball is never going to go up the hill by itself, but if we use an external force, we can move it to a direction, in a direction that will allow its potential energy to increase. And so that's what we kind of saw with those cases of the charges moving either with or against the electric field. That can help us understand why in some cases their potential energy would increase, where in other cases it would decrease. So hopefully this will help. At least it'll entertain you for a little bit on this snowy day.